When we all right, so when we describe an amplifier, we always speak about the gain, the input impedance, and the output impedance. So we know that the voltage follower has got one key characteristic, is that its voltage gain is unity. But what about its input impedance and output impedance characteristics? So remember here, when we speak about an operational amplifier, it already has a built-in input impedance Zin, right? And an open loop, and that's what we're going to refer to as open loop input impedance. We already have an open loop gain, and we already have a output impedance. We already have an output impedance that we're going to refer to as open loop output impedance. But now, when we start speaking about the voltage follower, we're not just talking about the operational amplifier itself, meaning the input impedance and output impedance I'm referring to here are no longer the open loop ones. Here I'm talking about the closed loop input impedance and output impedance, because by adding extra stuff to the operational amplifier, we automatically change its input and output impedance. So we'll have to redraw the voltage follower and therefore reassess its input impedance, closed loop now, and the output impedance. So with a voltage follower, we have a feedback network that goes from the output. So let's assume that the non-inverting, the inverting input of the amplifier, the non-inverting input is here, and that way we apply our input signal V in, and on the non-inverting input, in the case of voltage follower, we just have a feedback of 0 ohm from the non-inverting pin to the output pin of the amplifier. Now, how much overall input impedance do we have? Closed loop input impedance in this case. The closed loop input impedance in this case, for us to understand how to calculate it, as well as the overall closed loop output impedance, so Z in closed loop and Z out closed loop, we need to go back a bit to a generic negative feedback type of amplifier, meaning to an amplifier with an inverting amplifier network, and assess that. So if we go back to an inverting amplifier network, whereby we've got a virtual ground and we have RF feedback resistor, we've got an input resistance Ri, and we've got the input signal applied there, V in. Then if we go back to this and we try to reassess what is the closed loop input impedance, we'll know that from inside the amplifier there will be an open loop input impedance all the way to ground. Now, with this point, so now when we say closed loop input impedance, we are trying to assess the input impedance from the input side, point inward, looking into the amplifier itself, closed loop. So that will be a combination basically of R in, then we've got a virtual ground, then we've got Z in closed loop, open loop, all the way to ground. The fact that these two are grounds, the fact that those two are grounds is more like these two lines were connected together. So we basically end up with Ri in series with 0 in parallel with Z in open loop. These two in parallel will just result in R in parallel with a short circuit, meaning all the way to ground. So at the end of the day, Z in closed loop is just equal to Z in closed loop is simply equals to R in, or almost equals to R in. So the closed loop input impedance of an amplifier is just R in. Now, in this case, as we mentioned when we're studying the follower, the Z in closed loop being almost equal to R in. What did we say about the follower? We said it has got R in, which is almost equal to infinite open circuit, because we said the fact that we don't draw R in is because we are assuming a very high R in, right? Infinite. So that's why we say the closed loop input impedance of a voltage follower is extremely high. At the same time, when it comes to the output impedance, closed loop output impedance of an amplifier circuit, the closed loop output impedance of an amplifier circuit, or Z out closed loop, it also has to be assessed by connecting all the other parameters configured with the amplifier. And I'll just avoid you the derivation of this, but at the end of the day, the closed loop output impedance of an amplifier is equal to the output impedance open loop, the one seen inside the amplifier, divided by 1 plus the open loop gain multiplied by a parameter that the textbook calls beta, but to avoid confusion with the beta that we know of a transistor, we're going to use beta A, or amplifier beta. The beta A here in this case is actually what we call the feedback fraction. Okay. Why feedback fraction? Because it determines how much of the output signal get fed back to the input. So it's the ratio that shows how much of the output signal get fed back to the input. And beta A therefore is computed as Ri divided by Ri plus Rf. Right. So taking that into account, in our case Ri, in the case of a voltage follower, Ri is infinite, Rf is 0. So that leads to beta A being equal to Ri being very big. It's gonna be alpha almost over alpha, which will be like 1, right? Infinite over infinite, which is almost 1. And that makes the the closed loop output impedance of a voltage follower to be nothing but the open loop output impedance divided by 1 plus the open loop gain multiplied by 1. Now the open loop gain of any operational amplifiers we know, of a good operational amplifiers we know, has to be a very high number. It's normally a very high number. So whenever you divide, and Z out is normally a very small number. So now, when you've got a very small number divided by 1 plus a very high number, you obviously get a very, very low number. So that's why we say the output impedance of a voltage follower is normally very small and normally approximated to 0, almost 0 basically. Okay.